Okay, so we are recording, so keep your comments safe.
Katie and I both passed.
Congratulations. And Marcelo has a backpack soon.
I do have a backpack today.
Okay, so you guys should have your foldable.
I like your outfit, Marcelo. What else to do?
Okay. So, this unit starts our fourth out of 4 units of study for statistics. So this is our inference unit. Okay. So hypothesis testing is a part of the inference unit. The rest of the time from here until May, we're going to be talking about different types of inference. So we kind of did our probability, now we're going to do inference. So under the what is a hypothesis test? So we're going to do an inference unit, so what in the world is inference? So inference means thank you for that circular definition.
To infer means to guess upon what.
Well, it means to make a decision based on data from a sample or an experiment.
That's pretty close to this.
So we've talked about how to get those samples, how to perform an experiment. We've talked about what is the probability of certain things happening. Now we're going to put all of that together and see what do we do with the results. Once we've done this, how can we use it to infer something about the results? So that's what we're going to be doing. We have 2 different types of inference. We have confidence interval and hypothesis test. Each of those is a part of the inference. And they kind of tie together, and we'll talk about that as we go through here. But a confidence interval and usually we'll just abbreviate that as CI so we don't have to write out confidence interval. It uses data from a sample or experiment to make an estimate about a population parameter. So this one is kind of saying, well, if I want to estimate the percent of people who have brown hair, I'm going to say it's between 60 and 90%. So there's an estimate, okay? That's what we're doing with the confidence interval. We're saying, well, I think it's going to be somewhere around this. So it's giving an estimate. Sometimes it's really precise. Sometimes it's not so precise. You can say the percent of students who drive to school is somewhere between 0 and 100%. Well, that's probably an accurate estimate, but it's not very helpful. Because it's like, okay, well, that didn't really tell me anything. So our job is to find a good estimate, something that's going to be helpful in making a statement about that population parameter. So for a hypothesis test, We're going to start with a belief about a population parameter. Population parameter, and then we will gather data using either a sample or an experiment to determine to test the belief. So we start with something we think is true, and we're going to gather some data to test it. Then we're going to determine whether the results are due to random chance. So is this something that would naturally occur? We know if we're looking at samples of students and looking at the average GPA of those students, if we get one sample of 20 students and we get another sample of 20 students, those aren't going to be the same average GPA, but they're probably going to be close. So we want to know, is the difference in what we expected and the results that we're getting, is that just a random chance difference, or is it like really different than what we expected? And then we use that information to make a decision on whether the data supports the original belief. So that's kind of the shortened version. I will warn you now, I'll try to be upfront with you. These can be a little lengthy when we go to writing them out. So get ready. But we just follow a step-by-step process. We have a 6-step process that we'll follow, and you just do all 6 steps. You'll do them the same for this entire unit. Every single different type of hypothesis test we do has those same 6 steps. So you'll get to where you know those steps really well, so you're just doing them. So, but it's like doing 6 problems in one, because you have to do something here, and all the way through. So I'm warning you up front. Get ready to write. It's exciting.
That's my excited.
That's your excited. Okay, so parameter and hypothesis. So for starting with hypothesis, we said we first start with a belief about a population parameter. So the parameter is the true value. And it's going to be either a mean or a proportion. So you would need to distinguish which one are we talking about for this problem and be able to define it in terms of the problem. Remember, it is always estimating a value for the population. Population goes with parameter, sample with statistic. So if we calculate it from a sample, that's a statistic. If we calculate from the population, that's a parameter. So if we're doing means, our notation is mu. That's what we use for the mean. If it's a proportion, we either use p or pi. I usually just use p, but some textbooks, some online material you may see will use pi for proportion.
That seems confusing.
They just use all Greek letters whenever they're dealing with population. And so that's just the Greek letter they choose. Like mean is mu, so proportion, pi. They just use it as a Greek letter instead of as a value of pi. Okay. So this you should already know. This is one of the first things we did back in August, September, is defining what the parameter is. What's our population? What's our parameter? This you should know. Okay. Null hypothesis. This is the notation. Is written as H sub 0. So that's our null hypothesis, is H with a subscript of 0. This one will always use an equal sign. Okay? That's when that certain problems make it sound like you should do an inequality there, but you never do an inequality. It's always an equal sign for HO. Everything is exactly what we expected it to be. We think that this is happening, and that's what's happening. We expect this, and this is what we got. That's what you're looking for, is what did we expect to happen, and that's what we're going to say is HO. Our alternative is written as H sub A. So we have a ho and a ha. So this H sub A is our alternative. H sub O is the null. Most of the time, I just write it using this notation. I don't write out the alternative hypothesis is. I'll just write HA. This one is a statement of change. It's different. Or something is going on. So here we'll use a less than or a greater than or not equal to. We never use an inclusive inequality. We will never say less than or equal to, because the equal is always up here in the null, and this is always some sort of inequality. Okay, it has to be inequality here. And we'll talk about one-tail and two-tail tests. If it's a one-tail, think of it like when we were doing our normal model. It could be that we shaded here. or it could be that we shaded here. Either of those is a one tail. Okay? This would be a less than, this would be a greater than. So when we're talking about this up here, these two are the one tail. The not equal to means it could be more, it could be less, but it's just not equal. So this one is going to be our two tail. These are going to be one tail. Only one tail is shaded. This is two tailed because both of them are shaded. So we're saying we think it's here, but if it gets far enough away, we're saying it's not there anymore. Something is wrong because it's not where we thought it would be. You doing good so far? Okay, so let's look at some examples down here. So we're going to write a hypothesis for each situation. So number one says a package delivery service claims it takes an average of 24 hours to send a package from New York to San Francisco. An independent consumer agency is doing a study to test the truth of this claim, as there have been several complaints about the company not meeting its delivery times. So, to write this out, we need to first of all define what is the parameter we're looking at. Are we looking at an average or a proportion? Yeah, because it says here, average of 24 hours. That tells me I'm looking for a mean. I'm looking for an average. Okay? So there should be something in the problem that tells you which one you're doing. So we're going to define what that is. Since it's a mean, we're going to use mu. And this is the true average. Hours. To deliver a package. And if you wanted to write out from New York to San Francisco, that's going to be fine. That's what we're from New York to San Francisco. So that's what we're defining. So we're going back to where we had to define our parameter, define our proportion, all of those things. You need to be able to remember those. So here, this is the parameter of interest. So once we have that, HO is always the equal sign. It's what do we think is true? What is the claim to truth? The claim is it takes 24 hours. So the claim is that the mean is 24. Our alternative is, well, if that's not true, then what do we think is happening? And they're saying that they're not meeting the delivery time. So does that mean it took longer or shorter time? Longer. That's when there's a problem, is when it's longer. So we're testing to see, is it really longer than 24 hours? Does this make sense to you why it's a greater than? You have to think, when would it not do this? When would it be a problem? And that's how we're going to define this. Okay, number 2. Says a team of eye surgeons has developed a new technique for risky eye operations to restore the sight of people blinded by a certain disease. Under the old method, it is known only 30% of patients who undergo the operation recover their eyesight. Can we justify the claim that the new method is better than the old one? So are we dealing with means or proportions? Proportions. How do you know that?
Because it doesn't say the average.
Never does it say average. And we have this percent. Percents are typically proportions. Okay? So we'll want to define, instead of doing mu like we did up here, we're going to do p. So p will be the true proportion. I can only talk so long until I start coughing now. I've kind of hit the point. So what do we think is true? I've got a whole bag full of them in here. I'll explain in a minute. So what is the standard of how many patients recover their eyesight? 30%. That's going to be what we put here. So that's what has been happening. That's what is expected.
I don't think I would ever hear this observation.
Well, if you don't get the operation, your chance of recovering is 0.
Fair point.
So, we want to justify that the new method is better than the old. So are we going to say greater than, less than, or not equal? We're still going to get 0.3. Are we going to say this is more than 0.3, less than 0.3, or just not equal to 0.3? We want to say the new one is better. So more people are recovering. So this one's going to be a greater. Does that make sense to you? So more people will recover their eyesight now than did before.
So technically speaking, about the population, statistics. So you have to have an
Just keep going until it works.
Yeah, that's what I do.
Okay, number 3. In 1990, 86.3% of the populations of Cortland, New York, were natives of New York State. Has the percentage of native New Yorkers changed since 1990? So, are we dealing with means or proportions?
I'm going to go proportions.
Yes, as they said, percentage, proportions. Good. So what am I going to use to define this? True proportion.
Alright, that's all I got. Of percentage let's say percentage of population natives, like around that gist.
Yes.
Yeah, true.
You're in the gist.
That's close enough. I got the first 4 words right. Guess what? That's like 12%.
So our null hypothesis is the one with our equal sign. So we're going to say P equals what?
86.3.
This one is still P, is still the number. We just have to figure out what goes in between there.
Less than.
Now we just want it's changed. Not equal. Look at you. Okay, so what I'm going to do, I'm going to give you guys, each table is going to get one of these lovely things that has 4 different problems. You're just doing what we just did right there. And you're writing them over here on the your turn to practice. You'll do one in each of those squares for these.
I don't know, Miss Kimberly. I don't think you should walk around and hand those out. We want to make sure you have a good recovery. So maybe we should hold back on that. We just want to make sure you have a good recovery.
People don't believe that people your age whine this much.
They did.
The only people that are listening to it are people who are
Unless I just decide to send it to your parents and be like, hey, I should just
my parents will be
videos
surprised.
that you should watch.
See, that is a valid argument, though.
But here's the
That's
thing.
the argument I made with you the other day. I was like, tempted to like.
Rather than you guys trying to talk me out of handing these out, you could have said, you know what, Miss Kimberly, let me do that for you because you know what, you're kind of not feeling good. I can take that and hand it out for you.
Okay, Josh, you're even right next to her desk, Brady.
Exactly.
Send this to her. Hey.
Brady's mom would care if she were able to hear the whining and complaining.
Right? Get smacked across there. She'd get washed.